evening and welcome back, everybody. My name is Seth McGowan, Vice President of the Adirondack Sky Center and Observatory, and I'll be your host this evening. The Adirondack Sky Center and Observatory is proud to bring you the next presentation in the Cygnus series. This series of live virtuals and interactive educational presentations takes place each Friday night at 7 o'clock, and we've developed this Cygnus series as a way to continue our educational mission during this period of social distancing and limited gatherings. Of course, we hope to do these again live at some point, but until then, please check back each week through Columbus Day weekend for a new lecture. In the same spirit, we are now officially doing live virtual interactive stargazing, so we'll be sending out notices, and they'll be of the pop-up nature. So look for those via email on a Facebook page and so forth of when those will take place. So for those of you who might be new to the Adirondack Sky Center and Observatory, you'll notice our location, which is perfectly suited for astronomy given our Class 4 boreal skies, but it doesn't stop just there. Our Astro Science Center is currently under development and will become an important destination for all ages in the future. Our numerous interactive exhibits within the museum will educate and thrill visitors as we Earth beings continue our exploration into space. In addition to the exhibit hall and continuing our hands-on approach to astronomy is our makerspace and interactive learning experience where visitors will engage in virtual reality, telescope making, and much, much more. Our spacious lecture hall will be a great place for large groups to hear about the wonders of space. And our premier state-of-the-art digital planetarium will take you on trips beyond your imagination. We invite you to be part of this exciting future by becoming a member of the Adirondack Sky Center and Observatory, and consider a gift to help make the Astro Science Center a reality. And now on with tonight's presentation. But before we begin, you'll notice that your microphones are muted. This is our practice to ensure the enjoyment for all who are with us. But I'd ask you to feel free to ask questions. This is an interactive talk tonight, so feel free at any time to unmute yourselves and ask a question of our presenter. Tonight's presentation, as well as all of our talks, are available on YouTube at our YouTube channel, and you'll be provided with links for those in the chat area tonight. So now it's my pleasure to welcome back to the Cygnus series Jeff Miller, Adirondack Sky Center and Observatory board member and St. Lawrence University astronomer and laboratory coordinator for tonight's presentation, the Equinox, Facts and Myths. Take it away, Jeff.
All right, thank you, Seth. So nice to see everybody here. Back again, hopefully. If you came to my first talk, which was way back in August, seems like years ago. So as Seth said, I'm an astronomer at St. Lawrence University. I've been there for 3 decades now, starting my 4th decade. Hopefully I get to retire before I complete that decade as well. And I am a board member of the Sky Center. If you were at my last talk, I started off with a similar theme for my PowerPoint. I decided to leave this here because my lonely astronomer here staring up is definitely experiencing some neck problems by this point. So my talk tonight, the Equinox, Facts and Myths. We know that there's an event coming up next week. We're going to talk about what that means, what causes it, and some myths that are surround this particular event. So first of all, I always like to start with this slide where because I do use the entire screen, just a suggestion that may help you to be able to see all the screen. And there's a lot of different settings in Zoom you could play around with. So kind of the default setting when you come in is you may actually see a grid button to the right of this. You might see, you're probably in this view with this button selected here, and you see a whole column of people here. And then once again, you can see one of my most ardent fans always comes to my talks. What you might want to do is click the single button, the single fat button next to it. That way you're just looking at my lovely face. I did remember to shave today, so it's all good. Or if you just want to hear the lovely tones and soothing tones in my voice, click that. And that way it just makes sure that my image is not blocking anything on your screen. Okay, so autumn is coming. We could feel that there's definitely a chill in the air. I've had to readjust the settings on my thermostat. Keep turning the heat up. In the last couple of days, I've actually turned on the seat heaters in the car in the morning. So what's going on? Well, we know that autumn starts, the first day of the fall season starts September 22nd. That's this coming Tuesday at 9:30. It seems pretty odd. Why are we so specific about that time? So why do we say the 22nd? Why at 9:30? What actually happens? Is this some particular event that just appears on our calendar, or is something celestial actually occurring? That's what we're going to take a look at. Now, if we were doing this as a real talk where I could stand in front of an audience, I would be holding one of these celestial spheres. We have a whole laboratory filled with these that we use for our introductory astronomy students. And this is really nice because it gives us kind of a view that the classical Greek astronomers had of the universe. The Earth at the center. You can see the Earth is upright here, unlike most globes that you see. And this clear plastic sphere around it that has some stars painted on it. So when you go outside and you look at the sky at night, on a nice clear night, you see all of the different stars and different objects. And as far as you're concerned, yeah, they might be different brightnesses, but they all look like they're just painted on the sky. And that's what this celestial sphere represents. Here's a picture from one of my textbooks that just kind of shows the different parts, some of the important positions that we mark on here. Now you'll notice in the center of my picture and in the center of the celestial sphere itself, there's a little tiny Earth. And you can see that the equator is drawn on the Earth and it separates the northern hemisphere. We're actually right about here. You can see the North American continent there. And we see underneath we have the southern hemisphere. What we have to remember now is we know that we're going from summer into fall, but in the southern hemisphere, the seasons are reversed. And that's kind of odd. They're going from winter into spring. Well, we're going to talk about that in a few minutes as well. There's some markings on here. So first of all, if you were to take the Earth's equator and kind of draw a line in that same position on the sky, we still call it an equator, but it's a celestial equator. It's an equator that we draw on the sky. When you go back to my celestial sphere, you'll notice the celestial equator is where the two halves of plastic are actually glued together. So you can think about that. It's the northern hemisphere and the southern hemisphere of the sky. That's where the seam is. That's where they're glued together. That is the celestial equator. And that's just directly above the Earth's equator in the sky. Now there's this other funny line here that's tilted at an angle, and it's got a strange name. It's called the ecliptic. And you see that it's tilted at an angle, and here on this picture it shows an angle of 23.5 degrees. We're going to come back to that number in a few minutes. The ecliptic is the sun's apparent path in the sky. We know that over the course of the year, the sun will change its position against the background stars. Now, remember, we now know we have the benefit of thousands of years of scientific research. We know that we are actually orbiting around the sun. But if you were standing here on the Earth and you didn't know that we were moving, it looks like the sun is orbiting around us. So if we were to trace its path over the course of the year, this is where it would follow, the ecliptic. Okay, we're going to come back to that in a second. You'll also notice that the ecliptic and the celestial equator cross at 2 points, right here and right here. Over on this side, the ecliptic is well above the celestial equator. Here, it's below. 2 more markings on here. You'll notice that we know that the North Pole of the Earth, the North Geographic Poles up at the top, and there's a dashed line here, touches the celestial sphere, and we call that the North Celestial Pole. If you go back to my celestial sphere model, you'll see there's an axle that goes right through the axis of rotation. It's the point where the Earth rotates, and that's where it hits the sky. So you know that there's a big axle goes straight through the Earth. Where it touches the sky, that's where we call the North Celestial Pole. If you can see the region of the sky around the North Celestial Pole, over the course of the night, the stars will all orbit around that position. Somebody, if they would like to unmute themselves, who knows the name of the star that marks very close to the position of the North Celestial Pole? Anybody want to take a guess?
The North Star.
The North Star, excellent. Thank you very much. We also call that star Polaris, and that's why that star is so important, because it's very close to the North Celestial Pole. So if we can spot Polaris in the sky, and stars of the Big Dipper point right to it, then we know where the axis of rotation on the sky is. Unfortunately, there's no, you can see there's also a South Celestial Pole. There's no bright star that marks the South Celestial Pole, but there's some nearby constellations that help us find it. Now, the other thing I want to point out here, you see all the little white flecks on here that represents the stars on the celestial sphere, just like they're painted right on the sky here. But these little pink arrows remind you of the fact that even though if we stand outside, it looks like all the stars are the same distance, they can actually be at very different distances from us, okay? All right, so let's take another look at the celestial sphere. But now, remember I said that the ecliptic marked the position of the path of the sun over the course of the year. So we see that the 2 points here where the ecliptic and the celestial equator cross, that's what we call an equinox. And over here, and there's some arrows that show the direction of the sun over the course of the year. Around March 21st, that's the spring equinox. It's what we consider the first day of spring. When the sun gets here around June 21st, we call this a solstice. And the solstice, we're going to look at what those words mean in a minute. We can see that that the sun is at its highest point above the celestial equator. That's the first day of summer, the summer solstice, around June 21st. We're coming up to this position here, the fall equinox in September, again crossing the celestial equator. And then in a few months, we'll be at the winter solstice, the start of winter, okay? And that's around December 21st. So you can see as the sun travels around over here, occasionally it marks these various positions. That's how we know when the seasons start. But you might look at that and you say, I wonder if everybody in the whole world uses these same names for these positions. Would you think, who wants to try to answer that? Do you think that everybody in the entire world talks about the event that's coming up as the fall equinox, or in December as the winter solstice? Somebody like to take a try at answering that? Anybody have any ideas? Well, remember that, I made that text so that my friends in Australia could read it. The seasons are reversed in the Southern Hemisphere. So in December, if you were in Australia, it's summertime. It's a great place to visit in the middle of our winter. So it's becoming much more common to refer to these events by the month, not the season, because all of these seasons represent what we would see if we're here in the Northern Hemisphere. So we refer to the June solstice, the September equinox, December solstice, and March equinox. Okay, so that's kind of neat. Now, something else you might notice on here is that I said that the equinox that's coming up is on Tuesday. That's the 22nd. Wait a minute, this is a picture from my textbook. You can see the copyright here. It says September 21st. Is my calendar wrong? Did I make a mistake? I make mistakes all the time. I made a mistake in my lab instructions this week, and I didn't find it for 2 days till one of my colleagues said, hey, you've got the wrong answers there. So I make mistakes all the time. Well, it turns out, no, that's correct. Astronomers always remember the 21st, June, September, December, March, as the start of the seasons for the solstices and the equinoxes. But it turns out it's been like 1,000 years since the March equinox was on the 21st. And that's because we know that there are 365 days in our year, but it actually takes the Earth 365 and a quarter days to go around the sun once. That's why every 4 years we have a leap year. So things have kind of gotten out of whack a little bit. That's okay. So sometimes a solstice or an equinox might be the 21st, the 22nd, sometimes the 23rd. It's all good, all right? But astronomers, we always remember the 21st. Okay, so let's take a look at the definition of those words, equinox and solstice. Equinox comes from the Latin root that means equal night. That means we have the same amount of daylight and nighttime, 12 hours. So on Tuesday, we'll have roughly 12 hours of daylight, 12 hours of nighttime. It's not exact, and well, that's a whole other talk that we can go into the reasons for that, but it's pretty close. The equinoxes occur in March and September. The sun, remember, is crossing the celestial equator. The point of the equinox is when it's directly on it. And on those days, the sun will rise due east and set due west. Solstice comes from the words that mean the sun stands still. If you were to plot the position of the sun every day at noon, it doesn't seem to move very much in its position on the sky at noon near a solstice. So it looks like it's standing still. Other times of the year, it will change its position in the sky quite rapidly from one day to the next. So at this point in June, it's when the sun is at its highest point in the sky. In December, it'll be at its lowest point in the sky. And when the sun rises or sets, it'll be furthest north or south of east. It doesn't rise due east or set due west. And we will also have many more hours or many fewer hours than 12 hours of daylight, depending upon which solstice we're at. That's kind of cool. Okay, now, if we were in a planetarium, we would see something like this. I've taken some screenshots from the planetarium program that I use called Starry Night. And we have some lines on here that I'll explain. So we've got this green line that goes across this way. We have another red line here. You might see, oh, in this particular screenshot, we've got the planet Mercury there as well. Also, I have a few constellations highlighted. Well, if I put some labels here, here is the ecliptic. So this is the sun's apparent path through the course of a year in the sky. And there is the sun. You can see the little yellow dot. Now, this is what we would see if we could turn the brightness of the sky down so that we could actually see the background stars. Astronomers know where the sun is with respect to the background stars all the time, even if we can't see them in the middle of the day. Now, you might notice that the names of these constellations are familiar. Cancer, Leo, Virgo, Libra. These are the signs of the zodiac. The ecliptic, the sun's path, goes right through all 12. Well, there's actually 13. That's another discussion too. All these constellations of the zodiac. And here you can see that the celestial equator and the ecliptic are crossing. Now, one other mark that I've put on here is, if you notice in the upper left-hand corner of the screenshot, it says the date and the time. So I started this one at the beginning of this month, September 1st at 9:30 in the morning. So I'm just going to show you a few shots, and we're going to see how the sun actually changes its position from one day to the next. So this was the beginning of the month, and now this is September 18th. This is this morning. At 9:30, you can see that the sun has moved here. It's much closer to the celestial equator, but hasn't quite gotten there yet. The 22nd, this is Tuesday, 9:30. At 9:30 in the morning, you're going to feel a cosmic thump, and that is when the sun trips over the celestial equator. By the end of the month, September 30th, it has moved on. So if we go back one, on the morning at 9:30 in the morning of Tuesday, that is when the sun is directly crossing the celestial equator. That marks the equinox. So any time that you see on your calendar that it is an equinox, the start of fall or the start of spring, the sun is crossing the celestial equator. So there is actual physical meaning for it, at least according to astronomers. Okay, so we know now, as I said, keep having to turn the thermostat up. It's getting cold. The days are getting shorter and the temperature is getting colder. So what's going on? If you spent any time this summer camping or even just around a fire pit in your yard, you know that when you are standing close to the fire, it's very warm. Sometimes it gets too hot. And so you back away and it gets much cooler. So you might think, well, maybe we're moving farther away from the sun. But why are we moving farther away from sun? I thought we're just orbiting around the sun. That's kind of crazy. Are we just flinging around in random orbits? Well, let's take a look at what it looks like. If you were with us a couple of weeks ago, Meg Thatcher talked about the moon, and she talked about how the fact that the moon, when it's orbiting the Earth, sometimes it's a little bit closer, sometimes it's farther away. The path that the moon takes around the Earth is elliptical, looks like a squashed oval. Turns out that all the planets orbiting the sun also travel in elliptical orbits. This was discovered by Johannes Kepler, who was a, whoops, there we go. Hit the wrong thing there. There we go. This was discovered by Johannes Kepler. He was a German mathematician, lived in the late early 1600s. He was the one who figured out that the orbits of the planets around the sun were not circular, that they were actually elliptical. Turns out you can pretty closely approximate them with a circle, okay? And I know everybody these days complains about having to wear a mask. Imagine having to walk around wearing a collar like that and this on your wrists. Yeah, that would get tiresome real fast. So what Kepler found is because planets orbit around the sun in an elliptical orbit, sometimes we can be a little bit closer to the sun, sometimes farther away. Now, I do want to emphasize, I drew this picture. This is not to scale, okay? This squished oval here is much more exaggerated than the actual orbit of the Earth around the sun. But it gives us the idea that, yeah, sometimes we are actually closer to the sun, sometimes we're farther away. Okay, so I have a pop quiz here for you. I am going to show you a question. This is interactive time for people. I'm going to show you a question and then a poll is going to show up on your screen so that you can actually try to answer this question and we'll see what people think. Here is my question. We know that it is warmer for us in June than in December. So the question for you is, when the Earth is here at its closest point to the sun, is this June or is it December? So you should see a poll question here. Take a moment and click on it and we'll see what we have. Now, this is an anonymous poll, so don't worry if you get the wrong answer. That's why we're all here. We're going to try and figure all this stuff out. Okay. Oh, this is cool. It's telling me the percentage that's voted. Everybody's excited about this. You got a chance to wake up and click the mouse. Oh, this is awesome. Oh, I love this. This is great. I'm watching how the poll is running. This is really nice. Okay, almost got everybody in. How about that? I wish I could get nearly 100% participation from my students. This is excellent. Okay, so, guess what? We are pretty much tied. We have 48% of people said that this is June, and 52% of people said that this is December. That's pretty cool. Okay, well, it turns out, all right, I'm going to end the poll. This is why we're here. It turns out that we are actually closer to the sun in December. Remember, in the southern hemisphere, the seasons are reversed. So when we are really cold in December, it's beach weather in Australia. We know that the average distance from the sun, from the Earth to the sun, is about 93 million miles. At our closest point in December, we're at about 91.4, close to 91.5 million miles. At our farthest distance, we're 94.5 million miles. I didn't have to marry a mathematician to know that I can subtract those two numbers and see that I have about a 3 million mile difference. You say, wait a minute, Jeff, we're 3 million miles closer to the sun in December. Why is it so darn cold in December? That's bizarre. There must be something else that affects our weather besides how close we are to the sun. And 3 million miles, it sounds like a lot. I know I get tired just driving to Canton, and that's 10 miles from here, okay? Well, don't get to drive very much anymore. 3 million miles compared to 90 plus million miles, it's nothing. This distance has very little effect on the temperature of the Earth. There's something else that actually affects it more. And that is the fact that the Earth is tilted on its axis. Anytime you buy a globe, you see a picture of an Earth globe, it's tilted like this. Well, it's not just artistically stylish, there's a reason for it. Remember, I showed you the picture of the celestial equator, right? Which would be the Earth's equator, but out here on the sky, and the ecliptic. They're at two angles with respect to each other. Anybody remember what that angle was?
23 and a half.
23 and a half.
23.
Excellent. 23 and a half. Excellent. Very good. People were paying attention. Nobody's asleep yet. Okay. 23 and a half degrees. Now, that angle, the ecliptic, not only do you find the sun there, but you find all of our planets there as well. Sometimes we call that the plane of our solar system. Kind of like if you put all these marbles on your desktop that represented all the planets, they would all be sitting on that desktop. And it's because the light is hitting the Earth at different angles. That is what causes the Earth to get hotter, or portions of it to get hotter during certain times of the year and colder at other times. So here, see here, we said the angle actually changes. And it turns out we know that light carries energy. And anybody who has a dog or a cat knows that they like to do solar physics experiments. They love to just lie in the sunshine, okay? So it turns out that what we can do, I've got a demo here. Let's see if I'm gonna do this. All right, everybody, whoops, there are my glasses. Here we go. You're looking at my desk. Hopefully everybody can see this now. I'm gonna put this right here. Let's stick this back a little bit. And what I have is, there we go, just a black sheet in front of me. I'm gonna turn off my desk lamp because I want this dark for now. And I have an impartial observer here. He's gonna keep an eye on me. Here's Einstein, keeping track of what's going on. Now, I have a flashlight here. Now, if I am, let me try, does that work? Yeah, that works. Okay, now you can see I'm holding this flashlight. Here's my flashlight, holding it straight above the black sheet. And hopefully you can see that there is this small circle. Right now, the light from my flashlight is shining directly on this black sheet, making this concentrated circle. We know that whatever energy is coming from this light will be absorbed by this black sheet. Obviously, it's a lot less energy than what you would get if you were dealing with the sun. Now, this is when the angle is very direct on the surface. If I take my flashlight and tip it at a very extreme angle, can you see that what had been a small circle is now a large oval? Can everybody see that? Okay, so the same amount of energy that was concentrated here is now spread out over a larger area. If you take that same amount of energy, spread it out over a larger area, well, you're not going to get as much energy in here. And you know what? It's going to get colder. Okay, so That's pretty cool. Normally I would do that on a blackboard or in my, or just on the wall. So let's go back to the presentation now. And let's take a look at a computer simulation of how the sun is actually striking the surface of the Earth as it orbits around. Created this again with Starry Night. We're going to let this go around once, and then we'll take a look and see what happens in more detail. Notice how the tilt of the Earth stays in the same direction. It's pointing this way. Well, at least on my screen, it's pointing that way. Okay, movie's going to pause. When it starts up, I'm going to stop it for a sec. And there we go. Now, notice here's the sun, here's the Earth, obviously very exaggerated in size. But notice that the sunlight is directly striking the southern hemisphere of the Earth. This is when it's really warm in Australia. Notice how you're not getting as much sunlight up here in the northern hemisphere. This is when it's cold. This is December for the Earth. This is approximately the position of the December solstice. Now, I'm going to move the Earth around some more. We'll let it continue and we'll stop it here. This is an equinox. Well, we can't really see anything right now because we happen to be on the outside of the Earth. It's actually making an eclipse, which again is another topic for discussion. Let's continue it over to this side here. Now, notice, remember, the tilt of the Earth has remained the same. It's always pointed in that direction. But now, notice how the sunlight is more directly striking the northern hemisphere of the Earth. This is the June solstice. This is when it's summer for us, winter for the Australians. So we had winter, we had our spring, our summer, and now, and now we're coming up to, that went all the way around. Let's try one more time. And now we're coming around to our fall, right here, another equinox. And from here, from this point, can you see how the Earth seems to be evenly illuminated? The sun is pretty close to directly above the Earth's equator in this model, okay? One more view of that. So this was an animation, came with my textbook, shows us basically the same thing. Here's the same position on the top, but on the bottom here, I'm going to pause this right here. On the bottom, so the top is exactly what we saw before. On the bottom, they have some arrows. If you had the Earth upright, how would the sunlight be striking the Earth? At an equinox, it's striking it directly, look, right above the Earth's equator. As we continue, we're coming into the northern hemisphere summer. So this is the solstice in June. Look at how the sunlight now is striking directly on the northern hemisphere. Come around, and now we're coming back to the next equinox, which is where we are in September, again striking us directly. But it's on its way down. Now we're heading towards December. And now the sunlight is going to be striking us at a much larger angle in the northern hemisphere, much more directly in the southern hemisphere. So it's the tilt of the Earth on its axis. That is what causes our seasons, not the distance of the Earth from the sun. Pretty cool. Glad we've learned something today. Now, I can show you all the computer models, and I could draw you all kinds of pictures, but how about we look at some actual photos to see how the position of the sun changes in the sky. Let me turn my light back on so you can see me again. So what we have here, this image, this is from the astronomy picture of the day, and these photos were actually taken, you might be able to see in small print down at the bottom. These were taken back in 2007, 2008, and I'm pretty sure that every year at one of the equinoxes, the astronomy picture of the day shows the same picture. It was taken by a Turkish amateur astronomer. His name is Tunça Tezel, and he has actually taken a lot of really magnificent astronomical photos. He took this one in Bursa, Turkey. It turns out the latitude, how far north of the equator you are, of the latitude of his position there is almost exactly the same as the latitude of New York City, about 40 degrees north. Up here in the North Country, we're getting close to 45 degrees north. If you come and visit me, I'll bring you up to Messina, a few towns north of here, and you get to see the big sign. You get to pose by the big sign that says that you're now at the 45th parallel and you are halfway between the equator and the North Pole. So basically his picture, even though he's in the east, right? He's in Turkey. This is basically what we would see in our sky. Now, we have a whole bunch of images here. What did he do? He took pictures of the sun at an equal interval of time on 3 separate days. Now, he used a very special camera lens. It's called a fisheye lens. This entire circle here is your horizon. It's your surroundings. And I've put east, south, and west. So notice, this looks like, I don't know, a tower or a chimney, and you can see the ground. You can see some mountains. There's a TV antenna, okay? There's some apartments down here, and there's more trees and buildings. And so this is the entire horizon, and the camera is looking straight up above our heads. Remember, that point is called the zenith point. The sun will rise in the east, set in the west, and down in this direction is due south. Due north would be up here. I didn't bother to mark it. So what he did during 3 days of the year, he took a photo of the sun every hour on the hour. So each one of these images is a picture of the sun separated by 1 hour of time. The 3 days that he chose was the June solstice. One of the equinoxes, it turns out it was the March equinox. He would get the same picture if he took it in the spring, in September, the September equinox, and the December solstice. So remember, on the equinox, the sun is rising due east, setting due west. At the June solstice, the beginning of our summer, it rises north of east, sets north of west. In the December solstice, the beginning of winter, it rises south of east, sets south of west. So remember that the zenith was here. So the higher up above the horizon that you go towards the zenith, zenith is 90 degrees. That's a right angle directly above your head. So you're going to higher and higher angles. So let's count how many days or how many hours of sunlight we have on each one of these 3 days. I've put, so if we start at 0 at the moment that the sun rises on the horizon, we see that there are 8 images of the sun here at the December solstice. That makes sense. We don't have very much sunlight during the day in the middle of winter. On an equinox, hopefully we find 12. Oh, how about that? There's 12 images of the sun from sunrise to sunset, equal times, equal day, equal night. And we should get a lot more than 12 hours, turns out, 16 hours of daylight in the summer. So we can tell that the sun is coming down closer to this point in the sky. And then as we go through winter, we're getting lower and lower angles. It's getting colder and less daylight during the day. So here we have actual photographic evidence of the change in the position of the sun over the course of the day. That's pretty cool. Now, let's get to some fun facts about the equinox. Here's the hallmark of what my discussion's about tonight. Can you only balance an egg on the equinox? Well, if I could, I'd be wasting my time tonight. So, turns out that that is not true. You can balance an egg any time of the year. Thing is, nobody ever does it, except maybe on the equinox. If you balanced an egg on the equinox, say, hey, what do you know? That myth is actually true. But nobody ever balances eggs in October or January or whenever they feel like it. These 2 pictures here, this is from Dr. Phil Plait back in October of 1998. He had started, he's an astronomer, and he had started with a blog which became a website called Bad Astronomy. And basically what he would do is point out bad astronomy mistakes in movies, and it started from there. He's still very active in the community. He still writes magazine articles. I think he writes for Discovery. Sometimes you see his articles in the newspaper. He does a lot of public outreach, and he was one of the people who, when I read his article, who found out what the source of the myth. Why did people start balancing eggs on the equinox? And what's the deal with that? So we're going to take a look at that. So first of all, this picture that I had started off just before, when did I take that? I took this one March 10th, back in 2018. I did this preparing for one of my astronomy classes. And it's like, well, the March equinox is the 21st, 22nd, something like that. But that's a couple of weeks ahead of time. And I started figuring out, you know, if I start balancing an egg on the first day of class back in January in the spring semester, that will really show that maybe, you know, there's really nothing to this myth. So I balance eggs all the time. This one I did 2 weeks ago. You can see it sitting on my counter. Now, typically I will use the counter in my kitchen, because about 5 years ago we had a renovation project, got a new kitchen. The kitchen counter is like the only level place in my house. My house is 145 years old, so I have very few level places. However, I'm going to try and attempt for you to balance an egg right here on my desktop. So I will have my impartial observer who will keep an eye on me, make sure I'm on the up and up, okay, that I'm not pulling anything shady. Okay, here I have my eggs. I actually have 2 eggs. I have a backup. I was really paranoid that I was going to break one. Oh, I left my iPad on the table here because my wife had said, you know, you ought to do something to convince people that, you know, you're actually doing this live, that you're not, that you didn't pre-record this. This is my iPad. Oh, there's Willow again. This is the current day, the current time, and you know that you cannot make Apple lie about anything. So this is live. You are seeing this now. So I'm going to take my egg. We'll see. I'll leave the light off for now. I can turn it back on. Here is my egg, just an ordinary egg. I'm going to balance it. Oop, I think I have to put my glasses on to do this. And I have to get closer so I can see what I'm doing. This is really hard to do when you got jittery hands and you've been busy talking. Let's cooperate. It's just building tension. Almost there. There we go.
Wow.
Let's try changing the angle here. There we go. Here, I'll even hit the autofocus. There's my egg.
Wow.
There we go. Einstein is making sure. There are no strings. There is nothing on the table. I was talking with Seth earlier. When we were kids, it was common. Yeah, you sprinkle some salt on there. You can do it. There we go. Okay, so before I move away from the document camera, and it is an ordinary egg. If anybody would like to see, I did bring a bowl. Later, we can break the egg. Nothing on there. Okay, so before we move away from the document camera, I'm going to put my egg away so I don't smash it on my desk. I want to show you one of the things. Now, remember, Dr. Phil Plait, I showed you the picture of him before, and he found out what the source of this myth was. I think I'm going to rotate the camera so you can see this. All right, let's try a little more autofocus. Try to get this in here. Now, anybody who is over 50 years old remembers Life magazine. There we go. Okay, Al Crispo, I know you're watching. I know you remember Life. Okay, so this is a huge magazine. I brought in a Physics Today for comparison. This is a standard magazine. Look how much bigger this was. This used to be a weekly publication. This lasted until the 1970s. By that point, it was a monthly publication, oh, I guess I should probably try to flip it so you can actually see it. There we go. That's what I wanted to do. Sitting here looking at the camera. Okay, boy, trying to adjust these controls while you're talking is really hard. All right, anyway, this magazine, this issue, this is the source of, and 10 cents, holy smoke, that is the source of the myth. Well, let's take a look. Where did this come from? Here's the picture. So I bought this magazine, this issue, from this website, originallifemagazines.com. And if you notice, it is the March 19th issue from 1945, okay, wartime. So you look at the table of contents, all the remaining pictures here, I took pictures from inside of this magazine. Chinese eggs stand on end, page 36. Well, it turns out that there was an article there on page 36. It's called The Mysteries of the Upright Egg Dissolves War Tension in China by Annalee Jacoby. She was a very famous correspondent for Time and Life magazine during the war. You see, it's got this picture of somebody pointing to an egg that's balancing. She wrote about a Chinese ritual that welcomed spring. And the ritual is called Li Chun, and it was the first day of spring. And so a lot of people came to this city, Chongqing, where this event was going on, to balance eggs. It's a great way, you know, spring, sign of, you know, everything is starting to grow. Eggs, a sign of rebirth. So spring and eggs have always been commonly associated with each other. So what's going on? Where did this myth come from? And you can see we have a picture here of skeptic Albert Einstein. Well, if we zoom in on some of the text, it says that, you know, even in China, they didn't quite know where that origin was from. A couple of very old books, but they don't even know how old they are. The legend goes like this: one day each year, and that day changes just like Thanksgiving. And at a certain hour, winter goes and spring comes. This day is called Li Chun, or spring begins. For an hour before and an hour after the seasons change, eggs will stand on end. It came from these two very old publications. That's pretty wild. So that's only saying for about 2 hours before and after the equinox, you'd be able to balance an egg. So that would mean on Tuesday, I should be able to balance one from like 8:30 to 10:30 in the morning. Pretty weird. Flip another page and you get this picture of this gentleman who are balancing all of these eggs. The caption is below here, but I did highlight some of the text for you. It says, 35 eggs stand without support on the battered lawn of Chongqing's press hostel at a press conference. It's like, all right, look at this. There's nothing here but dirt and maybe some dead grass. That's not very impressive. My dog could balance eggs in that kind of soil. Well, no, she couldn't, because she would eat them all, okay? They even say the one in the foreground here is standing on its small end, on the pointy end. Not very impressive, okay? But one thing that's interesting about this picture, it says that this press conference where they're balancing these eggs was held on February 21st. February 21st, that's like a full month before the equinox. What's going on? I don't understand this. Well, it turns out in a lot of cultures and a lot of countries, the solstices and the equinoxes are not the starting points of the season, but are actually the midpoint of the season, the middle of the season. So by the time you hit March 21st, you've already gotten into spring. Makes a lot of sense. You start spring when things early on, maybe around February, just starting to warm up. Maybe you're getting through the worst of that February cold. And it turns out this festival of Li Chun occurs early in February. It's like a month and a half before the equinox. If you read the article closely, and nobody ever does, I know I get caught by that all the time. You read the headline, you read the intro, and then you move on. It says that the egg balancing started on February 4th and then was repeated through the month. They're not even trying to balance eggs just on the equinox. They're balancing for an entire month way before the equinox. So how did this myth become associated with you can only balance eggs on the equinox? What's going on? Well, remember, this is 1945. This is the end of World War II. Information did not travel as fast as it does today. Right now, if one of the Kardashians sneezes, you get a pop-up of it in 30 seconds. It took a long time for information to travel from China to the US and to get published and for people to get it. But it appeared in the March 19th edition of Life magazine. That's only a couple days before the equinox. And people started to say, oh yeah, I read about this and I could do this on the equinox. You put 2 and 2 together, you get 5, and there you go. You have a myth that is born. So to this day, if you go to Google, you do a Google image search for balance egg on equinox, you get page after page after page of people balancing eggs and people making videos and happy smiling children looking at eggs and decorating eggs and people outside balancing eggs. It's crazy. Has nothing to do with anything. Oh, and Google is even helpful because they will give you related searches. Broom standing up, what does that have to do with balancing eggs? Well, that's another myth that started a few years back. And it was one of those things that spread through Facebook that you could only balance a broom during the equinox. And then for a while, there was some strong solar flares. Oh, you can only balance a broom when there are strong solar flares. If you were with us for our discussion last week, Eileen O'Donoghue, who's one of our grand wizards at St. Lawrence, was shown here balancing a broom for the custodian's closet. It's not a big deal. If you take a broom where the bristles aren't really bashed, it turns out the design, the angle design, puts the center of mass in a point where it's actually really easy to balance a broom. Not very impressive, although it is always impressive when Eileen wears her wizard's cap at commencement and forces, you know, the students to march in line like this. It's always impressive. So the moral of the story is, obviously, whatever you read on Facebook, don't believe it, okay? Check things out for yourself. Wait a couple of months, try grabbing some eggs, try balancing some eggs, see if you can actually do it yourself. So I leave you again, once again, with a perspective image of what we would like to build for our museum, Adirondack Sky Center and Observatory, and I hope that you can help us out with our mission. Thank you very much, and if anybody has any questions, I'd be happy to answer them.
Thanks, Jeff.
Jeff, this is Al. I have one quick question.
Yeah.
Can I get a picture of Eileen with the broom?
Oh, I will sell that one to anybody who wants it.
Jeff, if I wasn't impressed before by you, I'm duly impressed now that you can balance an egg on a live broadcast. I think that.
Oh, and let me tell you, that's really hard. And I do it on the first day of my astronomy class. It's really hard when you're talking. It's like, oh man, I have to do this. So yeah, and I had that one egg that I balanced. I picked that out like 3 weeks ago because I've been testing eggs because there's no magic to it, but some eggs, just because of their shape, their design, they're easier to balance than others. Also, I found that letting them sit so that they can, have the broad end down, and so the yolk goes, oh yeah, how about that? It just balanced it again. Of course, now it was really easy to do it. So, but yeah, it takes practice, but that's it. You just got to practice. So.
Before we take some questions, I want to post some links for you in the chat area right now. Those are our website, our phone number, our email. and our YouTube channel, where this video, along with all of the others that we've done, will be posted tomorrow morning. And finally, as Jeff mentioned just a few minutes ago, the Adirondack Sky Center and Observatory, we're in the middle of a capital project for building our Astro Science Center. It's a $15+ million proposal, and we're hoping to get some support out there. And the link just went up. That Bloomerang link is to help us towards our goal in that campaign. And finally, before we take our questions, a little preview for you as participants tonight. You get the early link to next week's presentation, which is Dr. Valerie Rapson. She is a solar system ambassador, and she's going to be exploring the Zooniverse. So you can use that link down below and get in your registration early for that. So thanks. And let's go to some questions. Feel free to unmute.
I have a question for Jeff.
Yes.
Sometimes people talk about leap seconds being the special moment at which the Earth is still. Sometimes people say things happen on New Year's Eve, just before the time switches over to the new year. Is there any physical phenomenon that really does happen just at a specific time of year?
Things like that with leap seconds. We do have occasionally leap seconds because, you know, a leap year, yeah, it's 365 and a quarter days, but no, it's not exactly a quarter day. It's a little bit off. And so also basically the rotation rate of the Earth is changing very, very slowly. So every now and then we got to toss a second here or there. It's just compensating to keep our calendar in sync. Because if we didn't do that, eventually the point of the equinox might start happening in the middle of the winter, okay? Which is what happened, which is why we had, you know, a long time ago, why calendars were reformed. So the Earth doesn't stop, but it's just our way of keeping our calendar in sync with celestial events. So we have to do these little course corrections, if you will, periodically.
Does balancing eggs have to do anything with astronomy?
With astronomy, it's physics. It's all physics. And actually, Seth, can I share the screen again?
Yes, please go ahead.
Okay, let's do that. We'll share that. And let's get back to my document camera. And there's my egg once again. It's still balanced. Oops, now I'm upside down. Anyways, that's okay. All right. So, yeah, no, there's no physics. Obviously, ooh, you're seeing this sideways. That's cool. There we go. That's better. Okay. Yeah, it has to do with how well the shape of the egg, what we call its center of mass, where it actually relies with respect to the rest of the egg itself, and how well you can just get it to sit on its point. But there's nothing special about this. No glue, no salt, nothing on my table, okay? It's just a matter of just putting it there. So it's a balancing of forces. So obviously, if I have this egg which tips sideways, well, gravity is always pulling it down. So hopefully we can just, boom, look at that. See, now I can do it really fast. Okay, now the show is over. All right, so yeah, in terms of astronomy, the only thing that it's related to is, well, we have this association with the first day of spring as being something to do with you know, being able to, or the first day of fall, any equinox, being able to balance eggs. Nah, it's gravity. You can balance gravity anytime you want. You do that when you stand up and hopefully not fall over. Okay.
Hey, Jeff, this is Dan. I have a really I guess it's like a really easy question. I have two questions. I'll ask them both and then I'll mute. The first one is midnight tonight or tomorrow morning? And then and then the second question is what's up with like daylight savings time, and does that change the definition of the equinox, and how does that work? Thanks.
Well, first of all, I would like to correct you. It is daylight saving time. There is no S at the end of saving. So, and the only thing that daylight saving time would change is on your calendar or on your watch when the time of the event actually occurs on your watch, but it does not change the time that the actual event actually occurs. If you wanted to know whether you were looking, if you wanted to look at the sun, let's say with a solar safe telescope to see where it was in the sky at the moment of the equinox, you would just have to know what time to actually go out and see the event. So that's all that does. Daylight saving time is just an artificial construct that we have that just gets in the way of everything now. And as far as I'm concerned, midnight is the start of the next day. So midnight tonight is tomorrow. And that's why you always have assignments due electronically at 11:59 p.m. because people can't figure that out, students especially. Any other questions?
We do have a question about the tilt of the Earth from Jeanette.
Mm-hmm.
Hang on, I think she's going to unmute. Oh,
okay.
She says she can't unmute.
Oh, okay.
Let me. I'll just click the button here to ask her to unmute. Maybe that'll help. If that doesn't help, I'll ask on her behalf.
Okay.
The question is, does the Earth's 23.5-degree tilt ever move from that, or is it constant?
Maybe I'll save that for a discussion this winter. Okay, so let's say that 23.5 degrees is going to stay put for an extremely long time. It might vary over time, but it's going to stay at that angle. However, the north celestial pole, remember where the rotation axis of the Earth touches the sky. Right now it's close to Polaris, which we call the North Star. That is going to change. That's because if you've ever taken a top, you spin a top, and when it starts to slow down, it wobbles. That is actually what the Earth does. It'll keep the same angle, 23.5 degrees, and it might vary, but it'll keep that same angle, but it makes a slow rotation of where that axis is pointing, but it takes I think it's 26,000 years to do once. Okay, so it's really, really slow. The only people who care about that are astronomers, because we have to point our extremely large telescopes at very, very tiny areas of the sky. Telescope time is very expensive. So we have to know where that rotation axis is so that we can point our telescopes to the precise place and not waste time fishing all over the sky to try and find that faint fuzzy blur that we're looking for. So let's say that angle will pretty much stay put for a long time.
So if we align our telescopes tonight, we're okay for a couple of thousand years.
You're good. You're good. Yeah. So if you go back to Egyptian times, about 5,000 years ago, they talk about how the pyramids were constructed so that they were polar aligned with the North Star. Except the North Star in Egyptian times was not the star we call Polaris. It was another star called Thuban. And if one of these days when the world resumes its normal pace, you get to come to the observatory on a Friday or a Saturday night, whenever we're open, I'll show you where Thuban is in the sky. Okay, so you have to wait a few thousand years in order to be able to actually see that change. So, but Seth, we'll be good at the observatory for several hundred. We're fine.
Excellent. Glad to hear it.
Mm-hmm.
All right. Well, Jeff, I want to thank you again. This was a lot of fun. I will never forget your ability to balance an egg in public.
It's still balancing.
So that was great. Thank you
Actually,
again.
now I can take my hard-boiled egg and eat it for breakfast. So I'm
That
good.
sounds good to me. That sounds good to me. And you know, this is your second lecture for us. We appreciate that, and we'll be in touch about other events at the Astro Science Center. For everybody else, I'll put up one more time our capital campaign. We're looking for just a fantastic building with a museum, planetarium, classroom, lecture hall, a makerspace, and just fantastic exhibits being planned. So if you're interested in helping us towards that goal of $15 million, we'd be happy to talk to you more about that. You can reach us at AdirondackSkyCenter.org at any time. Next week, again, Valerie Rapson on Zooniverse, and the link is in the chat area, so feel free to register for that as soon as you like. And with that, I wish everybody good night and clear skies. Thank you.
Good night, everybody.
Good night.
Thank you very much.
Jeff.
Great
Excellent.
talk, Jeff. Enjoyed it.